Okay, we're off and running. Here we go. Here's the question. The first one is a standard sort of thing. Show that this is a factor of this complex polynomial. Well, that just means it. So here we go for part A. If Z minus I is a factor, then P of I should equal 0, all things being well. So we just have to check that. We get P of I is equal to that I to the power 4 minus I times Z. I instead of Z, put I plus I minus I. I to the 4 is 1 minus, that's I to the 3, I to the 4 as well. That's 1 plus I minus I, clearly equals 0. There we go. So that's very, very straightforward for the first part. But part B in this question was tricky and somewhat mean. This is the sort of thing you expect when you use the conjugate root theorem. If that is a root, you would perhaps be expecting negative I also to be a root from the conjugate root theorem. But in this question, it is not. That was the mean bit about this one. And that was because when you look at the polynomial itself, not all the coefficients are real numbers. In particular, look at that I in front of the Z cubed. And that means that the conjugate root theorem does not work. The conjugate root theorem only works if all the coefficients are real numbers. So for part B, you cannot use the conjugate root theorem. And that was the bit which, presumably this question was written designing to catch people out with that, because normally we would just, you've got one root, you can find the other one from the conjugate root theorem and it all works out easily for you. But this time you can't, because it only works for real numbers, real coefficients. Okay, having found that we can't use that, then you have to find, okay, well, how else will I go about doing that? There's two ways. And if I do one this way and one another way, here we go. First method. We have Z minus I is a factor. So if we can find the other factors, put it equal to 0, we can find the roots easy enough. We've got P of Z is equal to Z to the 4 minus I Z cubed plus Z minus I. Now, you could just do it by pausing for a moment. You could do it two ways. So that's a factor. Well, we can divide that into that, do long division, and find out what the other factors are. That's one way of doing it. Or you could do it and just look at the numbers we've got here. Sorry, not numbers, the expression we've got here, and just think, well, if this is a factor, well, I can see that, and it's there. I can sort of see that there because it's got a Z, it's got a minus I there. Think, oh, I can just factorize it straight away. So the first way you could just do that by looking at it, and you can see, oh, look, there's Z minus I. I multiply that by Z cubed. That would give me Z to the 4 and the I Z cubed. So that, and then you've got plus the Z minus I, and then we can factor out Z minus I with Z cubed plus 1. And that's it factorized. Or you could do long division. So that way is nice, but only nice if you just see it, just by looking at it. Perhaps more normally, we might just do Z minus I divide into. And you might be thinking, oh, golly, long division with I's and everything, it's going to be horrible. Well, sometimes it would be. It's not too bad this time. Z to the 4 minus I Z cubed plus Z. Oops. No Z squared plus Z minus I. You always got to have a column for each of the powers. Okay, Z into Z to the 4 goes Z3. Multiply back. That comes up, gives you Z to the 4. That times gives you minus I Z cubed, which is the same. So when you subtract there, you get nothing. And then it's just z minus I. There's no z squared into z minus I. It's plus 1 on the end. So it factors out quite quickly into the same thing. But you haven't finished yet, of course. From this, we get that I is one of the roots. We have to find all of the roots. We also have to make that lot equal to 0 and find what that value gives for z cubed. So I'm going to have to rub this off and do that on the next screen, but I'm recording this in super high definition. We'll see how that goes. Anyway, the next part is I'm going to have to solve when that equals 0. I've got it on the way. Part B, carry on. And this is just a standard, the routine for solving this one. So we get z cubed is -1. Z cubed then equals e to the I pi. Because e to the I pi gives you -1. Remember, you've got 1, -1, I, -I. You go around the diagram. Or add the 2n pi to give yourself lots and lots of solutions. Take the cube root of both sides. So z equals e to the I pi plus 2n pi. Over 3, and then we put n equal to 0, and we'll get z equals e to the I pi on 3. That's nothing. N equals 1. Z equals e to the I. 2 plus 1 is 3 pi on 3, which is e to the I pi. -1. And you can either go 2 or you can go to -1. I'll go 2. Z equals e to the I. Now, 4 plus 1 is 5 pi on 3. Now we're asked to have the answers in rectangular Cartesian form. So although this expression is nice and simple, e to the I pi on 3, and e to the I 5 pi on 3, they're nice, simple enough things. That's not sufficient for this question. We have to keep going to put them into rectangular. So here we go. This is the same as cos pi on 3 plus I sine pi on 3 equals half plus. There it is in Cartesian. This one at -1. Well, that's already that. It's just -1. And this is cos 5 pi on 3. So sine 5 pi on 3. 5 pi on 3 is in this quadrant here, so cosines will be positive, but sines will be negative. And there's our 3 solutions in rectangular Cartesian. And be careful to write your solutions then. So in this case, Z, your solutions are that one, and I, of course, because the I came from the first other thing. So you've got I, -1, half plus √3 on 2. There we go. Four lots, 4 solutions for it. Okay, that was routine, the second part. The really mean bit was giving you something where you could not use the conjugate root theorem. So I do this as an example just to watch out. It's got to be real numbers there for the conjugate root theorem to work. And if they're not there, then it doesn't work. Okay, I'm going to put a question up, and I'm going to leave it for a little bit. And whilst it's up there, I'll do a solution for that one that I'm asked to do. But here's the question I want you to have a look at. And I will, I'll pause the recording there whilst I just write that one up, because we don't need to record me writing it. Okay, there's that. There is the solution I've just done on the board for 117b. Boy, it was a bit long. I was probably, if I was doing it myself rather than doing it to show someone else very clearly what I'd done, I would have done it in a slightly, I'd have missed 1 or 2 of these lines here, but anyway, there is the solution for that particular one. So there we go, and I've just recorded it, so you can always look back at that when you need to start recording this solution again. Okay. So for this, we've got two things going on. We've got to find Z, given that is true and that is true. So there's two things, but presumably we'll have to combine the two at some stage to find out what our Z actually is. From this first one, as before, you're thinking that Z is X plus IY. So that's just a standard sort of way to do it, because then we can go to the Cartesian plane and start sketching things. Okay, we've got this, the modulus, well, that is the square root of X squared plus Y squared. That equals the square root. Now the real part is X plus 3 squared, and the imaginary part is Y minus 3. And then we did one of these already, but I'll keep going and see what we end up with. Won't be, that's interesting, isn't it? Anyway, we'll just square both sides and expand the brackets. The X squares go away and the Y squares go away. It's all on that side. So we got 0 equals 6x minus 6y plus 18. Divide everything by 6. 0 equals x minus y plus 3. Or we have the y equals x plus 3. Okay. Presumably, this bit here will tell us we're at one particular point along this line. Now we've done the first bit, now we'll do the second bit. And from the second part, we get I'll do it down here. We get the square root. I'll write the whole line of it in. We've got mod z minus 3i equals 3 root 2. This gives us the square root of x squared plus y minus 3 squared equals 3 root 2. Square both sides and expand the bracket. No, don't expand the bracket. Just square both sides. X squared plus y minus 3 squared equals 9 2s are 18. I didn't expand the bracket because we've got y minus 3 in here. And we substitute now in there, we put in x plus 3 in there, you'll see why I didn't expand that bracket. We have y equals x plus 3 from there. Therefore, we have x squared plus x plus 3 minus 3. I can see the plus 3 and the minus 3 we're going to go away. So we've got x squared, we've got 2x squared equals 18. X squared is 9 and x is plus or minus 3. Right, from that we can work out our two y values. X equals plus 3, y equals x plus 3, 3 plus 3, which is 6. X equals minus 3, y equals minus 3, 0. We've got two solutions. We've got 3, 6 and minus 3, 0. What does that mean Z is? Let's finish off the question properly. Therefore, Z equals, we've got our two solutions. We've got 3 plus 6i, or we've got minus 3, 0i. There's our two solutions at the end of that. So this was a modulus question which started off in the usual way. We find that line, but then brought in another little bit as well, just to I suppose make sure we knew what we were doing when we looked at it. Okay, I got one more question I want you to go. I've just been rummaging around old exam papers and finding questions that I thought were interesting for you. Here's another one. Once again, I'll stop the recording. You don't need to record me writing it up again. But when I put it up, have a go at that, and I'll give you 10 or 15 minutes and see how you go with it. Record of it. Here we go. I've done a little bit to start myself off. With this sort of thing, you always deal with things separate sides. And in this case, sometimes you start with the right-hand side and try and prove the left. But in this case, I'm going to take the left-hand side and show that it's the same as the right. Taking the left-hand side, the 1 plus root 3i, you can find the r. I'm going to change it into r e to the I theta. You can find the r using the standard way. You can find the theta, find with tan, and then you know what the angle is. So and that gives us that. for that expression, and I haven't gone through the whole thing, but it's the same sort of things, the same size. It's just the angle is down instead of up, and so for this we get 2e to the I pi by 3 to the n plus 2e to the I negative pi by 3 to the n. If you're not comfortable with this, I haven't done the whole thing for that one, but you do it in the same way as that part there. Okay, here we go. Let's just power of n will give us 2 to the n e to the I n pi by 3 plus 2 to the n e to the I negative n pi by 3. And from that, we can take out 2 to the n common. And here we have cos n pi by 3 plus I sine n pi by 3 plus cos, that's this bit here now, negative n pi by 3 I sine negative n pi by 3. This sort of stuff we do here, you'll begin to realise this turns up quite a lot. Like put the plus and the minus thing in, and all the minuses go away because the signs become minus and plus. It's a standard sort of thing to do with all this sort of question. Anyway, here we go. We get 2 to the n. That plus I sine pi by 3 minus I sine by 3. That take away that, it's nothing. And cos of a negative angle is the same as the cos of a positive angle. We end up with 2 cos n pi by 3. And that just gives us a solution, 2 to the n plus 1 cos n pi by 3, which equals the right-hand side as required. It is a standard sort of thing to do, give you the plus and the minus, and often the sign parts go away because of that. Stop that recording there. I'm trying not to make the recording too long, just because I'm doing it in that really, where's my mouse gone? There's my mouse gone. Oh, come on, mouse, come back to life. I'm doing it in that high definition. I don't want it to have too much stuff going on for it. It might upset the world. If I try and record too much high definition.